Thanks. I'll begin. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. I was going to send out an announcement. I told you already, Jonathan, but what was my announcement? Do you remember? Reading day. Yes, reading day by 2 p.m.
For what?
For mission. What mission are we on?
8
9. Yeah. So obviously mission 8 is due today. So I think I have them up here. And some of you have given them to me before break, which is great. So let me just try to wrap up the discussion about residue calculus. I think we have really just one little subtopic in some sense left, and that's the problem of fractional residues. And so here's the idea. You've got some curve, right? Whatever. And it's got singularities inside. There's some function f, is meromorphic. Near D. So here, this is D. The boundary of D is this guy, right? And then we want to add a wrinkle, and the wrinkle we want to add is suppose the f also has a singularity, right, on the edge. So suppose f has a singularity like, I don't know, here. But there exists, let's say, z naught in the boundary that we're integrating over, for which f has a pole, all right? And the question is, what do you do with that? I mean, it doesn't fall into the theorems we've given so far. So what you do is you trade the problem that you're after for a related problem that you can approach that problem in the limit. All right, so what we do is we just imagine encircling. Well, not really encircling, right? You imagine, let me make it a little bit simpler in terms of my picture at least. So suppose that this was actually like on a corner. All right? So it just happened to be like that. So what we imagine doing is, and I'm going to exaggerate it for the sake of this. Actually, let me exaggerate it down here so you can see better. So here's a singularity, and instead of course we can't just literally do that because, well, it's singular. So we have to approach it in some kind of sensible way, and the way we do that is we just make a little circle around it like that. All right. So let's see here. Is that right? Well, that one, I mean, I guess that is what I'd be dealing with, isn't it? I think my picture doesn't quite fit. Well, anyway, let's just do it. So if we look at this little arc, let's call that C epsilon, right? Where this is epsilon. As epsilon goes to 0, we should approach the integral over the boundary of D in the limit, right? So if we look at the modified D, let's say, continuing this pattern, let's say d epsilon, the boundary of d epsilon has the rounded edge, right? Then if we look at that contour, what can we do? If we don't, we replace the given d with one with this little corner kind of cut out like that, right? What's the difference between the given one and the rounded out one? Well, the rounded out one we can apply our previous result to, right? Because now the singularity is not on the edge of the modified contour, and so we can apply the residue theorem there, right? So we'd have the integral over the boundary of D, epsilon, of, let's see, how's it go, f of z dz is equal to 2 pi I sum of over, z zi in D singular, right? And residue of f of z zi, yeah? So the residue theorem. But then the thing is, we can look at this as what? This is equal to the integral over the boundary of d epsilon without that little corner piece, right? So that piece. And then plus the integral around the little corner piece, right? And the thing is, we can explicitly calculate the integral around the little corner piece and then take the limit as epsilon goes to 0. All right. So let's actually do that. So the integral along c epsilon of f of z dz, what would that actually look like? So I'm actually going to stick with my example rather than a general proof here, because I think it'll be more clear if I do it that way. You guys can actually tell me, how would I parameterize this c epsilon here? What would the parameterization of c epsilon be? And I probably should tell you that red x is z naught, right? So given that that's z naught, what's our parameterization? If I call this point here gamma of t is equal to what? It's equal to z naught plus epsilon e to the I t for what? What is my t range over there? Yeah, it's going. Well, that's what happened to us. Yeah. Oh, so you're like, I've written down a counterclockwise parameterization, so that's kind of hard to deal with, isn't it? Yeah, that's what you were going to tell me, I believe. So if I put a minus there, then it's clockwise, right? At least now it's a clockwise parameterization. And I think you can see we're swinging from minus pi over 2 less than or equal to t less than or equal to minus pi, I guess, would do it. Does that work?
It would be t from pi and then minus t.
Oh, so I want t ranges from pi over 2 to pi? All right. Okay, right. So explicitly then, this is equal to the integral from pi over 2 to pi of what we got. And if, so this, this is the other thing, is I only want to look at the part of f which is singular, because I know that the other part of f, which is non-singular, just integrates to 0 around the entirety of the curve. So I don't really care about that piece. So I want to focus my attention on the part of f, which is going to give a non-trivial integral. In particular, the piece of f, which is the residue, right? So, I have f of z is equal to something like, let's say b1 over z minus z naught plus stuff. I don't really care what the stuff is. The other stuff, when you integrate around a circle around the singularity, doesn't lead to anything. I mean, it does lead to something here, but that something would get caught up in the limit as epsilon goes to 0 of the other piece. So that's not the part I'm focused on. So let's just draw our attention to the b1 over z minus z naught, which in this case is what? I'm sorry, what is, well, z minus z naught is actually what? Epsilon e to the minus I, e to the minus it, and then I have the differential of z naught plus epsilon e to the minus it, right? Let's work that out. What's that give us? So b1 is a constant, and epsilon's a constant, we pull it out. And we were looking integral from pi over 2 to pi of what we got. There's an epsilon minus I e to the minus it dt, yeah? But of course, I also have division by e to the minus it. I should probably kept the epsilon in front. Pull that epsilon back inside so you can see what happens there. It just cancels. And the exponentials cancel, and we're just left with what? Minus I b1 integral from pi over 2 to pi dt. And what is that? Minus I b1 times pi over 2. So essentially what we've shown is that the singular part of the integral around the corner just leads us to a minus I b1. What is b1 though? b1 is the residue of f of z at z naught, yeah? Times pi over 2. Right? And then the thing is, when you add that to the other side, right? You add this to the other side, we get what? The integral, I mean, okay, fine. I mean, technically there's something else. There's another piece here, Pac-Man. All right, fine, I'll add it. You happy? There's the other piece I'm neglecting, the non-singular piece. And so to summarize the calculation here, and I'm starting to regret the amount of class time I've devoted to this. All right, but isn't that the case with everything I do? Let's see here, minus. By now you're not surprised. This is equal to, let's see here, I residue f of z at z naught times pi over 2. Of course, plus the 2 pi I, well, plus Pac-Man. I'm sorry, minus Pac-Man, I guess. Plus 2 pi I times sum of the residues. Where we're looking at the residues inside the contour. All right. So then what happens as epsilon goes to 0? As epsilon goes to 0, the length of C epsilon, right? The length of C epsilon does what? It shrinks to 0. And the piece of F which is non-singular can be bounded, right? And so so I'm arguing the singular part gives us the residue times pi over 2. The other part integrates to something that's bounded times something that's limiting to 0. So that the Pac-Man piece shrinks to 0 as epsilon goes to 0. And as epsilon goes to 0, of course, this just becomes the boundary of D itself. And then there we have the result, the integral over the boundary of D is equal to 2 pi I times the sum of the residues inside times this plus this fractional residue piece. And I seem to have lost something. I think, like I'm supposed to get, this is supposed to work out to 2 pi I times the residue at the edge, all right? And then times the arc length subtended divided by 2 pi. Oh, that is what we have, though. Okay, good. So the point is that when when the residue is inside, in some sense, this calculation is a special case. You get the full residue when the singularity is on the inside. When you're not on the inside, when the residue is on the edge, you get as much angle. You get the fraction of the angle that's subtended around the residue relative to the curve, and that's what you do. Yeah. So here I'm talking about. If you look at this is the alpha I'm talking about. Is this one right here? A different example. It might have something like that, and your singularity might be here. This might be, I don't know, what's that? It looks like pi over 2 again. Dang it. All right. Jump. There we go, better. All right, so now we got like pi over 3 maybe, something like that. And so if your f of z is holomorphic inside, and the only singularity for f of z happens to be that z naught right there, and this curve, this Pac-Man curve, let's call it c, then the integral along c of f of z dz, the fractional residue theorem says it's 2 pi I times the residue of f of z at z naught, all right, times what? Times pi over 3 divided by 2 pi.
Are we doing the exterior?
Oh yeah, thank you. Pi over 3 is not the one I want, is it? Very good, just as I intended. So you guys are paying attention. Excellent. So 2 pi minus pi over 3 is what I should put there, obviously. Yeah, thank you. There's a lot of 2 pi's in that, yeah.
So it's not negative over there or anything, it's just like the size of the angle?
Right.
In this case, it would be negative because it's clockwise.
The angle that you want to put, 2 pi minus pi over 3 is positive.
Right, but I mean, your C is out the positive boundary, right? So you're getting
Oh, did I do that? Because I didn't want to do that. So sorry. I was trying to do the counterclockwise, right? So it's all right. I have, as you know, I get disoriented. So it's that time of the semester, you know. Es bueno.
I'm confused, one's positive over there.
Philly. Why? Which one's positive?
It's the alpha, so it doesn't matter, like it would not, that alpha would never be negative for any case.
Right. I'm taking alpha to be just the angle subtended. I mean, maybe we need to look at some more examples in terms of if the singularity is here, then we imagine bubbling it like that. So here alpha would be equal to pi. If the singularity was just on a corner like this, all right, then again, alpha equals to pi over 2. If, oh, man. I guess it matters. It matters whether or not that corner, that's ambiguous without writing the rest of it, right? Because this and this are different. So that one has alpha equals to pi over 2. This one would have alpha equals to 3 pi over 2. And I think I need to make both of those counterclockwise, the larger curves. Hey, let's look at an actual example with a function in it, yeah? Do. So you guys have a good break? You found your way back, I see. You don't look too tired. So it's good, I think. Did you get tons of stuff done? I know I didn't. Yeah, fun things got done. Would you see equally? Would you see equally as many win as lose? Thank you for that, Sam. I like your perspective. All right, I will eventually find the notes here. All right, here we go. See, I don't think I watched any football, but it's not terribly surprising.
You watched the parade?
Oh, I did watch some of the parade, yeah. I was amused. There was a Goku float. It's a giant helium Goku going down the Macy's Thanksgiving Day. What's that? What's that? How dare you? What's that? What's that? It's like, who's Shakespeare? I don't know. Who's Shakespeare? What? So apparently I said something rather disparaging about Aristotle about a couple weeks ago, and it's finally found its way to like Dr. Skambordis. And he's like, some student emailed me that you said something about Aristotle in your class. Is that true? And I was like, yeah.
I'm pretty sure Morgan included it at the end of a math club email.
I mean, you know, of course, if I was alive at the time, what would I have been? I've probably been like a, I don't know, carpenter or whatever. I obviously would not have been writing physical law at the time. So, I mean, there is value to what he did. If he hadn't done horribly, horribly wrong physics, we never would have had Galileo to come along and fix his mistakes. But at the same time, there are other ancients who were much better physicists, like Archimedes. So I just don't understand why we don't talk more about Archimedes. If we're going to talk about an ancient physicist, Archimedes is an ancient physicist. Aristotle is an ancient philosopher who only did marginally useful things. I'm alienating my Greek audience right now. Yeah. So I think
I didn't know what that was.
Yes, Dragon Ball Z. Yes, that is So the joy of the Thanksgiving Day parade for me was this giant Goku float. I mean, it's one of those like, you know, those giant, helium things they do. And then listening to Al Roker try to say Saiyan. Because obviously he is not well versed in the finer things. He does not know about Saiyans and Super Saiyans 2s and 3. S-A-I-S. I don't remember. It's like it's. Yeah. So when Al Roker read it, obviously he'd never heard the word said, and I can't even remember how he pronounced it, but it was wrong, and it amused me. What's that?
You have to meet phrase as because you would say it.
Yeah, I mean, I'm sure I am mispronouncing Super Saiyan as well because I'm not Japanese. But anyway, but yeah, I think I lost some points with Dr. Skambordis. I think he apparently holds Aristotle in some regard. Oh well.
This morning he was telling me that he was the teacher of Alexander the Great. I told him Alexander the Great was only 13 and a half. How much do you learn from?
Well, I guess Alexander the Great was, I mean, he's got great in the title. That's pretty good. Um,
I have a question.
yes.
So, since we're not technically integrating around the boundary, but we're doing, like, taking this limit of these circles like get smaller, would you call this a sort of principal value, or?
It is. I would say it's analogous to a principal value. Yeah. And I know it's what you're thinking about is the. Are you kind of thinking about the other integral that we were talking about?
No, I just.
Yeah. I mean, it's a fractional residue, and nevertheless, we can meaningfully calculate things from fractional residues like this one. If we look at this indented contour, as it's called, we can look at the integral of dz over z plus 1 times z minus I. This has a singularity at I and also at minus 1. So this, I is up here somewhere, right? Excuse me, over here somewhere. Over here somewhere. I'll get it eventually because I is on the imaginary axis and this is the real axis, right? The imaginary axis is like over here somewhere. And once R is big enough, I is definitely in the interior. And so, as we calculate the integral over gamma, which is the indented contour, I believe, we pick up two pieces. The one is from the interior residue yes, I do mean positive I. What's that? Goodness gracious. But on the other hand, where's my other piece? Come on. Seriously? I think I failed to understand what gamma is here. Well, gamma's the whole deal. Okay, well, I don't quite follow my calculation in the middle there, guys. I'm sorry. I feel like that.
Well, if epsilon's greater than 0, that is right for gamma.
Oh, okay. So that's true, but then gamma breaks down into the principal value of the integral along the real axis, right? Plus the integral over the C epsilon piece.
Right.
And then the other piece along the half circle arc just integrates to 0 by the usual estimate, which is given here. Integral along the half circle arc is less than or equal to pi r over r minus 1 squared, which goes to 0 as r goes to infinity. So the integral along that piece goes to 0. The integral from minus r to r, after you fill in the gap, you've got, well, it's not the integral, it's the principal value in the sense that you're approaching this is yet another use of principal value. It's doubly principal, I think, in the sense that it's approaching the interior singularity at minus 1 symmetrically from both sides, because the epsilon, you're going plus or minus epsilon on either side of minus 1 in that integration. And on the other hand, this is the fractional residue, and so we get that. So anyway, there is a weird example, fractional residue. Here's a slightly less weird example. You could do the, we had this, was this on a test or a quiz? I forget what I gave this, maybe did you give these guys in homework? I can't remember. Homework, yeah. So my point is you could, so this was, what was gamma of t? It was the circular arc from there to there. And I was integrating dz over z plus 2 over gamma. And I think what I'm arguing here is if you deform, let's see here. Oh, you can deform this circular arc to just to this v. And the reason I've pictured the deformation here with some colors. And it's not quite right. These should be fixed at these endpoints, should all be up there. My picture's not awesome. So sorry about that. But if you think about deforming you can basically take this curve and like deform down to that, and eventually you reach tiny arcs around z equals minus 2, each subtending 4 pi over 3 of arc. And so the fractional residue theorem says that integral over epsilon 0 of this is 4 pi I over 3, which is what we got by direct integration in the homework. So you can actually, if you think about it for a while, use this deformation, this fractional residue theorem in kind of weird ways. I'm going to move on. So there's a little bit more in this chapter. Jordan's lemma is interesting. You might need it for a problem. Exterior domains are really interesting. But up next is the argument principle. And so here's what the argument principle says. Suppose f is analytic on a domain D, and you've got a curve gamma in D such that the function is non-zero on the curve. Then if we integrate 1 over 2 pi I times the integral, 1 over 2 pi I times the integral over gamma of the derivative of f over f, it's equal to 1 over 2 pi I times the integral of the differential of the logarithm. This is the so-called logarithmic integral of f along z. At the moment, this is just a definition, all right? Now, the fact that this should be equal to that, that's just calculus. If you take the differential of the log of f of z, we get 1 over f of z times df dz by the chain rule. And that's this, right? So this is just notation, all right? But what's interesting, well, here's an example. So let's look at f of z equals z minus z naught to the n. And I actually integrated not over a circle, but what is this? This is more than just a circle. What is this? If k is a whole number, like 1 or 2, natural number, 1, 2, 3, whatever, this is actually a circle that's been covered k times, right? So you'd say such a circle has winding number k. We don't talk much about winding number in here, but maybe we should. Anyway, so if we calculate f prime over f, we get, of course, the product rule gives me that, and that simplifies to n over z minus z naught. Aha, well we know how to integrate that, but I actually just plug in the parameterization for the circle and do the integral, and we get nk. So what is n? What is k? Well, k is because we have a winding number k. N, why? Because n is what? The number of... Well, I guess I didn't tell you, right? N could be what? It could be minus 3, it could be 0, it could be 7. So this is either negative or positive or 0, depending on whether n is representing function having what? Like a repeated 0? Or it could just, what would happen? If n is equal to 0, it's constant at the point, right? So that would be 0. If n is negative, on the other hand, you get a negative value here. So that's maybe, this is just an example, but maybe that tells us what the significance of f prime over f integrated over dz is. It's counting, adjusting for winding number, the number of zeros or the number of poles inside gamma. See, because this function has either n zeros or a pole of order n. I should say a pole of order minus n. Fine. Because anyway. And in fact, this example is general in the following sense. We have this argument principle. If D is a bounded domain with piecewise smooth boundary, and f is a meromorphic function on D that extends to be analytic on the boundary of D, such that the function's non-zero on the boundary, then if we integrate this, if we calculate the logarithmic integral, what's it give us? It gives us the number of zeros inside the boundary of D minus the number of poles inside D, and adjusted for order. Like if there's a pole of order 3 inside D, that counts as n infinity being 3. If there's a 0 of order 7, that counts as n sub 0 being 7. So it counts the difference between the number of zeros and the number of poles, adjusting for multiplicity of the pole, or 0. Now here, I've eliminated the winding number part of the discussion, right? But there's a similar theorem that could be stated if D was actually like a multiple covering of the boundary of D. We'd multiply by the winding number k and get the same result. The k times this would be the more general result, which we don't talk about much in here. And the proof of this breaks down into two cases, right? Because either when you look at So to integrate this, right, what's the deal? This is what? This is, where are singularities for this possibly at? Either at what? Either at zeros or at poles, right? Either one of those could give us a singularity of the quotient of f prime over f. So to calculate the residues of this function inside D, we need to figure out, we need to calculate what's the residue of this at any zero or any pole for f. And that's what the proof involves looking at those two cases, either f having a zero or f having a pole. In both cases, we're going to calculate the residue, and then the residue theorem produces this result. That's the proof. So let's look at the calculation. So first of all, if z naught is a zero of order n, we learned that that means that f of z can be written as z minus z naught to the n times h of z, where h is holomorphic at z naught, right, and is non-zero. And so if you differentiate f by the product rule, you got these guys, right? And f of z down there is like that. So then what happens? Well, this simplifies to n over z minus z naught plus this piece over here, right? Now, h of z naught is non-zero, and h prime of z, I don't care. Whatever it is, who cares? The point is that this is non-singular, right? So this is the entire principal part at z naught. And so the residue of this at a zero of order n is just what? It's just n. So the residue of f prime over f at a zero of order n is n. And similarly, if we have a pole of order n, we can write f of z as h of z over z minus z naught to the n, which we can write as that. Again, differentiate, use the product rule, and look at what what's the principal part. So I differentiate, I simplify, algebra gives me minus n over z minus z naught, right? Now here, pole of order n gives us minus n as the residue at z naught, at that kind of z naught, right? So depending on whether z naught is a zero or a pole of order n, we get the residue as plus or minus n. Plus for the zero, minus for the pole. And then Cauchy's residue theorem finishes the argument. To calculate the integral over the boundary of D, we take 2 pi I times the sum of the residues. But the residues inside this consist precisely of where f either has a zero or a pole. And those are, exactly n sub k, where that's either, positive or negative, depending on whether or not it's a zero or a pole. And this is just the labeling. We're saying n sub naught is the total number of zeros counting multiplicity, and n sub infinity is the total number of poles counting multiplicity. It's like a doubled pole gives you n infinity equals to 2. Right? If you had a pole of order 2, you had 3 poles of order 1, then your n infinity would be what? Be 5, and so forth. Now, it's also useful because remember, this is kind of a really weird result, right? This integral, this logarithmic integral, somehow counts the number of zeros and number of poles for this function inside that region. That to me it's just a very weird result, right? But on the other hand, remember, we can identify it as being 1 over 2 pi I times the integral of the differential of the logarithm, right? So if we pick on that, we can come to another interpretation of the logarithmic integral. So, of course, we know that the log, is multiple valued. We can write like that. It's the natural log of the modulus of f of z plus I times the argument. So if we select a particular branch, we can calculate the differential of the logarithm. It's the differential of the log of the modulus plus the differential of the argument, right? And so the log of the modulus, this is actually, there's no trouble calculating that all the way around the curve, right? If you look at, there's no discontinuity, right? The natural log of the modulus of f of z, as long as f of z is non-zero on the curve, that you can differentiate everywhere. The derivative makes sense. There's no discontinuity in that function whatsoever. It doesn't have the problem that the other piece has, which is that the argument might jump across where you've selected your cut. Right? If the argument goes too far, then there's a jump discontinuity, and we can't really say it's the differential of one argument function all the way around the curve. In contrast, this does integrate around the curve to 0. And so here, if the curve is parametrized, from A to B, mapping to gamma, then the differential of the natural log of this is just natural log of that. I mean, we can just do, going back to our initial thoughts about integrals, right? So we have that. And so if the curve is closed, this just goes to 0. It's not interesting, is my point. On the other hand, the argument piece, well, that's rather different, right? So the integral around gamma of the differential of the argument, it gives you, I'm not sure I believe that. Yeah, I don't think this is true. I mean, the details of integrating the differential of the argument are subtle. It's calculating the change in the angle of f as you go around the curve, right? You can't just calculate that from the values at the endpoint. It's more complicated. But anyway, setting aside this which needs to be removed, I don't think that's true anyway. If we integrate the differential of the argument, we should get 2 pi times that, because this, again, the other piece, the log piece, goes away, and we just have that. All right. Now, here's an example. Suppose we're looking at z cubed plus 1, right? And we look at gamma of t being z naught plus re to the it, right? Let's see here. I'm going to be more specific. I'm actually looking at 2e to the it, right? All right, so let's picture it here. What's the function I'm looking at? F of z is what? Z cubed plus 1, right? So what I point out here is that if you look at f of gamma of t, what do you get? We get 8 e to the what? 3it, yeah? Plus 1. What does that what can you say about the change in the argument of that as t cycles from 0 to 2 pi? And look at this. This is, so my question is, what can you say about the argument of f of gamma of t? Right? I mean, directly, you could view this, right? It's a circle centered at where? 1, right? And it's got radius, what, 8? And how many times are you looping around? 1, 2, 3 times, right? So if we look at the integral of this over gamma, you can see that that should be 6 pi, right? Because if you look at how the net change in the angle for the argument of f of gamma of t, it's clearly 6 pi. But we also know that 6 pi is what? I mean, the argument, the theorem we just argument principle we just went through says that n0 minus n infinity is equal to 2 pi, words. Sorry, I have all these symbols, and I need to actually write down the theorem. Again, what was the integral? Integral of the differential of the logarithm of f of z over gamma, which was actually, we worked it out, the differential of the argument of f of gamma, f of z over gamma, right? And that was equal to what? 2 pi times n number of zeros minus the number of poles, right? So this is 0. Why? I mean, it should be clear to you that f of z equals z cubed plus 1 has no poles, right? It's a polynomial. It's entire. There's no singularities. What's interesting, though, is we've just argued that there are 3 zeros for z cubed plus 1 inside the circle of radius 2 without ever finding a single one of them. This is very sneaky. Now, can you guys find the zeros of this polynomial by direct calculation? I hope so. That might be a question on the final, right? That would be a reasonable question on the final. Factor z cubed plus 1. How would you do it? Plus 1? Plus 1? So we're looking for, this is what, z minus z1 times z minus z2 times z minus z3. And here z1 and z2 and z3 are what? They should be elements of the third roots of minus 1, right? Because z cubed plus 1 equals to 0 says z cubed is equal to minus 1, which says that z is an element of the third roots of minus 1. Now, what is minus 1? Minus 1 is e to the pi I. So this, for what it's worth, is e to the pi I over 3 times e to the 2 pi I over 3 times e to the pi I over 3, and then e to the 4 pi I over 3 times e to the pi I over 3. So this right here, guys, is the principal third root of minus 1. That gets me rolling, and then I multiply by the principal third root of unity to generate the other two solutions. And these 3 things are precisely the zeros which the argument principle told us existed without actually finding where they were. I mean, I could picture them. E to the pi over 3 is about here-ish, right? That seems wrong. I'm an idiot. What's wrong with me? If I plug in minus 1, does it work? Yeah. Minus 1 should be one of these. Is minus 1 one of these? Oh, okay. I feel better then. This is the picture I was starting to draw was bogus. So there's my minus 1. And then the other two solutions have to be conjugate, right? Because the polynomial is real. So this is my z2. This is my z1, I guess. Here's my z3. And the picture's not quite right. I mean, those are inside the circle of radius 2. But the neat thing is the argument principle allowed us to show that without actually, if your cubic polynomial was much worse, where you don't actually want to do the algebra, but you just need to show that the zeros exist in some region, this is a very, very nice tool to have to work with. Here's a more horrible example. If you look, sometimes calculating the argument is a pain. So here I'm looking at the circle of radius 1 centered at minus 1, right? And so from the work we just did by non-argument principle things, that'd be this circle, right? So this is my second circle. And what I've plotted here is not that circle. What this is a plot of is the image of f. It's the image of that circle under f. So when you feed the circle centered at -1 with radius 1 into F, you get this monstrosity, which then I've used technology to graph. And if you look at this, then you can see the change in the angle, right? The net change in the angle is 2 pi for this red curve, which shows you that we've encircled 1, 0, which is legit. That's what we did. See, the other 2 circles are over here. We didn't encircle them with that circle. Sorry if these arguments seem circular. Sorry, I'm an idiot. Oh, hey, check it out, a link. Aw, the internet got me again. All right, so on Wednesday, we will talk about our final topic of complex analysis for this semester, namely Rachets Theorem, or Rachets Theorem, if you're not versed in how to say French words, as I am often not. I mean, I was always, whenever my parents said, excuse my French when I was little, it meant something else. But anyway, this is a really neat theorem, and it's built over the argument principle again. But the punchline of this section is a 3 or 4 line, quick, beautiful, elegant proof of a fundamental theorem of algebra. That's going to be our stopping point for the complex analysis. After that, the floor is open. We will talk about how to do integration over the algebra. I'll try to help you with the homework problems that I've burdened you with. All right? So that's my plan. Hopefully this will not take all of Wednesday. I will use the projector rather than doing this. So, thanks.